The great Greek scientist Archimedes lived in Syracuse around 250 BC. And one day, the king came to Archimedes and asked him to determine whether a new crown that he had had commissioned was in fact made of pure gold, or if the goldsmith had cheated the king. So Archimedes thought on the problem, and as the story goes, he was sitting in the bathtub, thinking on it and considering the effect of water on submerged bodies when he realized his principle of buoyancy. And he leaps out of the bathtub crying, "Eureka!" meaning, "I've got it." And so excited is he takes no time to dress, but instead runs naked through the streets directly to the king to describe his idea. And here is the test that Archimedes performed. He manufactured a bar that he knew to be of pure gold, of exactly the same mass as the crown, got them to balance on a balance, and then submerged the balance in a tub of water. Now, a solid body submerged in water will experience a buoyant force, and in this case, the buoyant force upward on the crown happened to be slightly greater than the buoyant force upward on the gold bar, causing the balance to tip. So, what does this mean? All right, the masses of the two are the same, and the buoyant force on the crown is greater than the buoyant force on the gold bar. Archimedes' famous principle is that the magnitude of the upward buoyant force on an object is equal to the weight of the fluid displaced. Let's apply that to our problem here. So, if we know the buoyant force on the crown is greater than the buoyant force on the gold bar, and the buoyant force on the crown is equal to the weight of the fluid displaced, then this is the mass of the fluid displaced times little g. And that's then greater than the mass of the fluid displaced by the bar, times little g. And the mass of the fluid displaced can be represented as the density of that fluid, the water, times the volume of the fluid displaced. So VFD there, the volume of the fluid displaced. And then the volume of the fluid displaced will be identical to the volume of the object. So the volume of the object replaces volume of fluid displaced. And then the volume of the object can be replaced with the mass of the object divided by the density of the object, or the mean density of the object, m over rho. So mass over density here. So these are all values for the crown on the left and all values for the pure gold bar on the right. And what we see here is that little g cancels out, and the density of the water cancels out, and the masses of the two objects cancel out since we know those to be the same. And thus we conclude this relationship between the reciprocals of the densities. Let's just flip that around to conclude that the density of the crown must have been less than the density of the gold bar, meaning the density of the crown does not match the density of pure gold, meaning the crown is not pure gold. And the goldsmith had indeed cheated the king, as the king suspected. So Archimedes is celebrated for his discovery and for the service that he has done to the king. He becomes famous through all the lands. Now, some years later, the Romans invade and besiege the city of Syracuse. Archimedes, in the king's employ, comes to the city's defense and builds numerous siege engines and weapons used to amaze and bewilder the attacking Romans. But they do eventually breach the walls and take the city. And the Roman soldiers were instructed to find and capture Archimedes, the famous scientist. But that isn't exactly the way things worked out. When the soldiers came upon Archimedes in his study, they found him drawing circles and mathematical geometrical diagrams in the sand. And he was intensely focused on his work and distracted when the soldiers came in, not even realizing the danger that he was in. And so when they trod upon his diagrams and his mathematics, the scientist is said to have cried aloud, these were his last words, "Do not disturb my circles." The Romans, despite their instructions, slew Archimedes on the spot. So he was killed that day. Or was he?